third try's a charm. Monday, April 14th, CS 746. I'm going to go through classification examples and then assign a classification homework today. So here's our sample. Again, just a quick and dirty to point out what happened here. We tried to do an example on the Podium computer here. It got an error that mlextend library from which you tried to import things was not installed. I went here and I told it launch the Anaconda PowerShell prompt. In the Anaconda PowerShell prompt, I said conda install conda forge mlextend per the directions on Google. And turns out that I don't have permissions because Media Services installed it for me. So I'm just going to show this real briefly. This is what happens when you try to do it. This is how it starts installing your package that you want to plug in. And then when you finally get down to the bottom, it says you don't have permissions. So I'm switching back to my WSU laptop, and I'm going to run it off of this screen instead. So we're going to start by loading all sorts of libraries out here that we need for doing our different classifiers, so on and so forth, right? So we're going to make some data. We're going to use what's called the make blobs feature of sklearn, and we can literally say, you know, make some blobs, and we'll build in a two-dimensional space a set of data points. And it'll center one around, you know, the first coordinate and one around the other coordinate, and this random locations and so on and so forth. So we've got two obvious bits to classify, right? So now we're going to split that into a test train set, right? Training and testing data, because we're using simple algorithms here. And so we're going to have to be able to say, you know, in our real world information, we have to split into how much we're going to use with the test and how much we're going to do the training. So we've done that. Just split the data. Now we're going to go ahead and see how big is our data sets. There we go. On the X test and the Y test, this is how much we have in the features that we're going to use, right? I didn't check how many rows we have. I thought it was a two-dimensional. Yes, it is. Yeah. Okay. Well, we got 5,000 rows on there. So, okay. So now we're going to go ahead and do a dummy classifier. Again, dummy classifier just will say, you know, so I'm going to assign everything to one group, right? And when we run this, we get some warnings about there because there's some things out here where it's not classifying anything into a class because obviously it's putting everything in one class, right? So it's got some divide by zero warnings that we'll get on here, right? But we look at our actual results here and we say we told everything to put everything in class 1, right? And so we got great recall on class 1, terrible recall on class 0, right? We look at our dummy confusion matrix now. And what we can see is that, you know, we predicted everything, 752, 748. Amazingly enough, that is exactly what we had with our data, right? So 752 were predicted as class 1, even though they were actually in class 0, right? So now let's try naive Bayes. We'll use the naive Gaussian naive Bayes classifier. We train that. We make predictions with it on our test set. We see how well did it do. We can see it did pretty good on the precision recall F1 score. Everything is great, right? So we get our heat map on there and run that, and we can see that in this case, it pretty well perfectly classified everything using naive Bayes. Well, that makes sense because everything is well differentiated, well separated, right? And again, this is examples, right? We can use linear logistic regression to do it. Again, we have very well separated samples, so we should be able to see a pretty high degree of accuracy, recall, precision on this. Again, 1, 1, 1. Yep, perfectly. Everything worked great, right? If we were to take our random blobs and move the centers closer together so that there was significant overlap, we would start to see some errors in here, right? So, or if we were to take a bunch of random points and assign them, we could see plenty of errors, right? Here's support vector machine was our third one we used, right? Again, support vector, we're taking and trying to find in our blobs here, back up here, we're trying to find the line that best differentiates between these is the farthest from the closest points of either blob. So we'd see you expecting a diagonal line like that, right? Visualizing. Now, we're not going to actually see that in our diagrams, unfortunately, but we run our support vector machine, train the model. We look at our results, and there's our scores. Again, we've got the same precision recall F1, so it's perfect on these examples. We're not even going to bother drawing the example. Now we have another data set that we pull in. The sklearn breast cancer data set. Is going to be our next sample. And we can look at the description on there and look at the keys. Target
please,
classes,
we can
and so forth.
We can see a screen, please. We can see a screen.
We can't see the screen. What are we? Share. Is it there now? Yes. Okay. That's unfortunate. I thought I'd shared the screen from the very beginning. So let's scroll back then. Again, what we started with was to include the we needed to import the ML extend on the Podium computer. We're not able to do that, so we went back to the, that's where I screwed up and lost my stuff. So we created two blobs of data, well separated, and then we did simple dummy classifier, which is going to be wrong in all half the cases, naive Bayes, logistic regression, support vector machine, and now we're in the breast cancer data set to try to see if we can do some classification on these. And again, we've got two target classes. It's going to be not necessarily a balanced data set. We split it into the test train sets. We're going to do two equally sized train and test sets, so 50% ratio. We're going to get our correlation matrix and define a function to be able to build that. And then we'll display that, and boy, it's a mess, right? This is an example of not great graphics because you try to put too much information in one place and it just turns confusing. I had an even better example with the PUBG data set where I think we had a heat map that had over 1,000 things in each direction. And yeah, it's great to show wonderful things, but you can still see, what we're looking for is the absolute values of the correlation. So we've done absolute values. So things that are strongly positive, strongly negative are going to show up as green on this. And things that are weak, down at 0, are going to show up as dark red, right? So we're looking for things that are going to give us, here's our target, do they have it? What are the things that correlate strongly with that, but don't correlate strongly with other things? And you can see there's plenty of things that are highly correlated with each other. And there's plenty of uncorrelated things in there, right? So we're going to import the data set. Just print the description out just to show you what it is. We run naive Bayes on that. And we can see that we've got an F1 score of 95%, which is pretty good. Again, it's a moderately unbalanced data set, right? Well, extremely unbalanced, right? Logistic regression. see if this happens here. The logistic regression is an iterative, trying to fix it, and it says it failed to converge. So we had a data set that we were not able to deal with as well as we wanted to on there, but we can still make predictions with it. And we can see that what it got out to is actually still pretty good classification results, right? Support vector machines, same thing. We take a look at our values that we get on there, and we can see it's not as great as the other ones, right? In this case, logistic regression looks like the highest performing, focusing solely on the F1 scores, right? We want the total highest F1 scores for both case 0 and case 1, malignant and benign. We can see we got pretty high scores, but the SVM wasn't as useful as the others on the malignant case, right? We can also go ahead and just use a random forest on here. And we're going to take our fit on there and come up with our well, it's going to take it a while to run that random forest there. This is the thing here. We started the random forest, and now we tell it to do the training of the random forest, and you can see that it's still running. It's going to take it a while to run. I should not have clicked on run so fast. I should have showed you the output first, right? But it'll eventually finish. There we go. 33 minutes. Okay, we had multiple processors on this, so yeah, that's not necessarily accurate. Anyhow, so now we go down there, we look at our F1 scores. Area under the curve, of course, is another metric that I forgot to be bringing forward, but very good F1 scores. Area under the curve, 91, 96, and so this is giving us a pretty good result on there. We can also run k nearest neighbors as our classifier. And we run this. We try, first of all, to do k nearest neighbors. We have to ask ourselves, how many neighbors should we look at, right? And so on this example here, we can see that 5 is probably a good choice, right? We could go all the way out to 25 and get a little bit better, but that's a whole lot more compute. That's what we're using for not the greatest improvement in error rate, right? So now we can run our train set, and we can see area under the curve. F1 scores are going to be very high for this particular classifier as well. Yes. Yeah, higher K would give you a risk of overfitting your data as well. Yeah, yeah. Yeah. Although if you're doing SVM tricks and things like that, you can get more overfitting when you get too many things in there, get too many curves in there, yes. But any algorithm, you can get high risk of overfitting if you do the wrong things, right? Except for random forest, it's perfect. It's a joke. Decision trees. Decision trees, individual decision tree always overfits, right? All right, now where are we at here? So now we want to try to do some multi-class classification. Again, we're doing some blobs here. And we've told it to pick some random states with 4 centers, and because we've got more of them, we have a higher chance of things overlapping with each other, right? So we're going to see some errors. We're going to take our data. We're going to create that. We're also going to try to create a data set for imbalance classification, where we have much more of one than of the other. And there's the weighted amounts of each cluster that we're creating, right? So for multi-label, it's basically setting up different data sets for each of these. And we're basically just showing how we can do the data set creation at this point. So the example down here now is not actually going to run the classifications on these, you can go ahead and run it yourself on your own time if you want to. But we've now got at the bottom here, we basically are just visualizing some interesting data sets that you might find useful for doing multi-class classification and imbalanced classification data set techniques, right? And again, the code to do the classification is going to be real similar to what's already in the example. So you can go ahead and use that, mess around with it, understand it. That is not the assignment. But it could be. Some semester that will probably be the assignment. Go out there and finish this example, right? But we're going to do something different. Okay, that was the basic classification algorithms. Now, a little more examples on decision trees, right? Because remember, we built it in a random forest, but we didn't do any of the decision trees. What does a decision tree look like when we actually train it? So we're going to try this super simple data decision tree. We're going to use the iris data set, the basic hello world data science tree. We're going to look at and make a decision tree classifier, and we're going to run it. And interesting, because we didn't tell it to assign the output anywhere, it gave us the example of here's the decision tree classifier, right? So it's trying to help us out on there. So now we're going to visualize it. So we can have the text tree. We can export the tree as a text, or we can export it as a matplotlib. And so when we do the plot here, we can go ahead and tell it to fill in all of the things in the decision tree. So we start with a sepal length, and we're going to try to decide what species it is based on the sepal length, sepal width, and so on and so forth. So we say, well, if the sepal width length, of the classes we have in the iris data set, which one best classifies? Well, short sepal width or length is a great classifier for separating out the setosa, right? The small sepals was way off in the corner in our classification, right? So at our first level of the tree, we can already classify our Gini index on the setosa is pure at 1 split, right? In order to differentiate between versicolor and virginica, we have to now go out there and try to do another sample, because we have a Gini index of 0.5. It's basically just all of them stuffed in there, right? So now we go out there and we try to do that. And what we end up with is Gini indexes that are pretty good. But if you recall from the scatter plots of the data set, looking at the sepal width versus sepal length on there, there's still going to be some errors in classification on there. So but basically we're taking, feature 1, sepal length, feature 2, sepal width. We're finding a break point in there. We're dividing our tree into left and right halves. And then we're looking at how pure our indexes are. And if we were to go ahead and tell it we want to be more precise, we could let it just keep on going, right? So for instance, let's try it. Let's go ahead and set our max depth maybe to 4, right? Because we have 4 features in the iris data set. Now we look at our tree and we can see setosa split out quickly right away. We split on sepal width. We have a Gini index of 0.186, right? So now we split on sepal width again. We get our Gini index down to 0.041. Eventually we get down, our Gini index. In this case, we've only got a few samples. And so we don't have a very good split on this end here, right? We would have to actually keep going another level before our Gini index could get down to 0. But if we let it go without any limit at all, it'll eventually get, levels of purity. But we're looking at things like sepal length, sepal width, over and over through here, right? So in each case, it's finding those are the best classifiers. And it's going to keep reusing them because they're numeric values, and it can split onto different levels, right? So that's our quick and dirty example of a decision tree being built. And you can go ahead and download that and start playing around with, your depths and so on and so forth. You could, let's see. That's why we're only looking at sepal width and sepal length. We actually told it not to pay any attention to the other. No, wait, that's 2 colon. Yeah, so that's going to be. I think we cut out petal length and petal width on them. Yeah. Colon 2, yeah, so he dropped out. Yeah. 0 and 1 are gone. So we could probably not separate that out and see. Yeah. So play around with that in your own time. All right, so now the homework I'm going to assign, and for those of you that came in after I started lecturing, it's a short lecture today. I'm basically going through examples on classification. And then I'm assigning a homework now, and then we'll call it good, and there won't be any attendance. So I apologize for making everybody show up when I'm not taking attendance. But yeah, we'll get a recording out there too. I was also really surprised at the beginning. I realized that I haven't shared recordings of the last few lectures, and I'm surprised that no one's yelling at me for it. So you need to keep me honest on that and get those lectures posted. And then I can turn around, I can yell at Ajay and Harika, and then you can yell at other, people. And it can be just, yeah, all the way around the line. Anyhow, so homework. Our newest homework is ignore this clustering lab. We're going to do this later. It wasn't quite ready for prime time. Our homework is going to be the classification on there. So if I take my, there we go. This should be the one. Oops. What happened there? So you're going to submit your own homework. I would say you can go ahead and talk with each other. There's 2 parts. Try to relate it to stuff from your own life and then do the classification. So basically the first thing is we want to think about what is a classification task? What is a situation you've had to do in your job, in your life, in current events, things like that, for which classification would be an appropriate solution to understanding it. We have a nice massive cell where we just import all sorts of stuff. Again, if you haven't done ML extend work on your laptop yet, you will have to import it. And the way to do that is to use the down here, the Conda Anaconda, and I like to use the PowerShell prompt. And it comes up. The mouse is going crazy because my screens are arranged wrong. And we can just do Conda get ML extend, which I'm not, whatever, anyhow. I'm not going to do that because it's already installed here. But that's the way to get that installed. We covered multiple classification methods. We're going to use this auto imports.csv. Ignore this line for now. That was, was part of the clustering lab, which I decided I'm not ready to talk about yet. Or for this homework, you can use the auto imports.csv database that's here in the lecture, and is failed to download to my examples on this machine here. Cool. Anyhow, or since you're all working on projects with different data sets, you've probably already done some classification work for your project, right? So you may have already done this homework or large chunks of this homework just in the course of working on your project. If you have, you can go ahead and steal that from that data set, right? And say there's bonus points. Yeah, maybe we'll do that. Maybe. I don't know. We'll have bonus points at the bottom here. In any case, so here we're going to pull in the auto imports database. And this is, of course, executable, but I'm not going to bother doing it now. Auto imports 1. We look at that data. We can see that it's got basically, this is data from a few years ago. There were no electric vehicles in this data set. There were engine types, or where's the fuel? Fuel type, gas and diesel were the two different fuel types they had in this data set. We need to get a new one with, you know, gas, diesel, electric, and hydrogen. All 4 data types. Yeah. Is there, how many vehicles are out there with hydrogen power? 3 of them. Anyhow, so we're going to do some basic EDA on that. We're going to wrangle the data into shape. There are some errors in this data set. We're going to change the data representations, so on and so forth, as per these instructions here. So there are question marks in the data set. Just replace it with none. There are variables that really are floating point numbers that, you know, horsepower, so on and so forth, that should be treated as floating point numbers that are just listed as integers. So we're going to convert those to floating point. We're going to drop some things we don't care about. We're going to do the info. We're going to do data wrangling to prepare for classification. Oh, whatever. I didn't notice that until now. We're going to go ahead and use the dependent variable as a fuel type. We're going to try to classify our cars, you know, as whether they're using gas or diesel by looking at the other variables, right? This data set is also used to do a linear regression, where you can try to see if you can use the other features of the car to predict the price, the sale price, right? This is how this started off. We're going to do it for classification now. So we're going to use logistic regression. Again, we already did that in our example, classification example in class. So it should be easy to copy paste some code for that to get started. And of course, you can always ask ChatGPT for help, and it will give you a wrong answer, as it sometimes does. Yeah. So if you try to use ChatGPT, be aware, you know, you could just shoot yourself in the foot with that. I have the best ChatGPT story. I'll tell that later. Okay. I've probably already told it. Anyhow, then try using naive Bayes. Try using k-nearest neighbors. We don't need you to do both SVM and random forest, but if you want to do them both, you can, right? Remember, random forest and SVM, especially random forest, will probably take longer because it's doing a lot behind the scenes when it's building all those trees, right? And then go ahead and look at your confusion matrix, your classification report, your area under the curve. Then looking at your, you know, F1 scores, your area under the curve, which one did the best jobs, right? Some of them don't work. Try to see if you can do some description of what happened, why, right? Bonus points, is your data set imbalanced? Yes or no? Well, in fact, yes, there's a lot more gasoline-powered cars than there are diesel-powered cars in this data set. So it's an imbalanced data set, right? And then, so this is for bonus. You don't have to do this, but you get extra points on your homework if you do. Is the data set badly imbalanced, enough imbalanced you think it's worth trying to do something about it, to try to do some of our algorithms to deal with imbalanced data and try to fix it, right? So go ahead, and then if you want this bonus points, try to balance the data, use SMOTE, use, you know, TOMEC links, something like that, right? One of our techniques that we've talked about, and try to rebalance the data a little bit better and see if you get better results from your classification methods. And again, you know, some of these methods in 3.5 will be not very good. Some of them will be better than others, right? So pick one of the ones that really failed miserably and see if it does better. That is the homework. Homework number 5. Again, if you go out to the content out here, you will only see, you will go from homework 3 homework 5. This homework 4 is invisible to you at this point. The clustering lab was designed with trying to do some clustering techniques on the PUBG data set to see, which the students were that were more, which competitors were more successful than others. And when I went through and tried to do it last year, or when I went to start reviewing it for this presentation, I realized that it was very messy last semester because it was a GTA that created it 2 semesters ago. And I need to make sure I'd get a hold of that GTA. He knows who he is. And verify that we're ready to go on that before I actually present that. So we may or may not do big homework 4. Right? All right. So that is big homework. Now, are there any concerns, questions, or comments regarding the project? Is everybody proceeding apace? I know that we had some sessions last week to allow you to talk about your concerns with that. Again, Ajay and Hardik are going to be available on a regular basis, I hope, going forward. So if you're having issues with your project, not having problems making progress on it, you can certainly contact us at any time via email, or we'll try to have regularly scheduled times for you to come in and discuss things with them. I owe you a homework for the midterm for people who got misunderstandings on the questions and things like that. It's not ready yet, but I'll have it. I'll go be working on that this afternoon, I think. And otherwise, if there's any questions, I see everybody's looks awake, but no questions. I see some people looking bored. Yes, I have. For the confusion matrix, if you want to use sklearn in the homework, you can certainly do that. Yeah. The example used MLextend. It's not a tremendously difficult process to install it. So, just takes a couple minutes. Like you saw at the beginning of class, it takes probably about 3 or 4 minutes. Sorry. It's actually a Conda install. Let me go ahead and switch back to, I'm going to shut this down. Yeah, because we've installed everything through Anaconda. You can do a pip install, but the easy way to do it is to go basically up here to say, I Googled Anaconda install MLextend. And it says, well, this is easy. All you got to do is conda install MLextend. And you actually, if your default is probably you're looking at Conda Forge. So you just go out there and I said, start Anaconda PowerShell prompt. And again, down here at the search, you can say Anaconda. And since it was the last thing I looked for, it'll pop that up right away. Or you can do the Anaconda old ancient DOS prompt, right? Whichever you prefer. Conda install, Conda Forge, : MLextend, and away it goes. It gets here where it says solving environment, and it will sit for a few minutes as the rotator happens, and then it will go ahead and say, okay, I found my environment. I'm going to download these packages. It will start downloading these. It will have progress bars on all of them, fly across. This will all go very quickly, and then it will not say, you do not have write permission. This computer, I do not have write permission on the Anaconda because for some silly reason, well, I couldn't get it to install. So I actually asked Media Services to install it for me, and they did it using the administrator privileges. So we can't actually install MLextend on this Podium computer, but we can certainly show how we can try to install it. So simple. But if you prefer to use sklearn, go ahead. There's no requirement to use MLextend. You can find another package. That's the cool thing about open source. If there's a package you don't like, there's always another one that does almost the same thing. And it may do it better. It may do it worse. But it's up to you. Right? Man, I loved Perl back in the day. That was a That was a programming language. Okay. Recording and transcribing. So I'm going to end the lecture now. There is no attendance thing today. Turning in homework 5 will be sufficient for your attendance credit for today. So do homework 5. Stop recording.